Salam sejahtera and a good day. This topic is about the design and analysis of clinical and epidemiological studies. What are the application of this series of studies? Number one, the biostatistical procedure involved in this series of studies can be used for the summary and conclusions of a trend or change of trend in a population. It is most famous for the study of health and illness, particularly on patterns of health diseases and factors that influence these disease patterns. This enabled the understanding of the cause of disease, determining public health policies, treatments, control plans, the application of population-based information for decision-making about individual patients, and therefore clinical epidemiology. All this forms the cornerstone of evidence-based medicine. Apart from that, we also have survival analysis, mathematical models of epidemics, measuring and determining infectivity using all these biostatistical tools. In fact, these biostatistical tools are among the additional tools that will allow us to associate the etiology agent of HIV with the eventual disease and syndrome that they cause, which is AIDS in this case. The biostatistical procedure used in clinical epidemiological studies will also allow us to summarize results from a series of analyses and, to some extent, even extend to comparison of test methods. This is actually an example of a website whereby we can get a series of epidemiological calculators that allow us to perform a surveillance and epidemiological studies as well as comparing diagnostic tests and perform case study data. Do ensure that you check them out at this particular URL, which has been highlighted on this particular website. Let's take a look at one of the analyses that you can perform using tools from clinical epidemiological studies. This is a table, or rather a figure showing survival analysis. So survival analysis actually is being done in such a way that we'll be able to determine the median survival time of a particular population when they are exposed to a particular factor. In this case, this is actually a survival time of canine heart patients treated with and without furosemide. The lines in green show that the animals have been treated with furosemide, whereas the lines in blue tell us that the animals has been treated without furosemide. So in this case, it's clear that this is actually a stepwise graph with each step being the censored event. So a censored event can be any event of interest. It not necessarily be death. It could also be, let's say, emergence of disease or maybe recovery or any events of interest. As you can see here, the vertical axis is actually cumulative survival, ranging from 0% or 0 to 1 or 100%. Whereas the horizontal axis depicts a duration, which can be expressed in any time units. It could be seconds, minutes, days, years, or even longer. As you can see here, this survival function allows us to measure the median survival time, or that means the proportion of population that is still survive at 50%. So in this case, on 50% of the population survive on somewhere around day 300, even if they are not treated with furosemide. However, if they are treated with furosemide, we can see that 50% of the population was still surviving as of close to 1,000 days. So we can see here the benefit of using furosemide as treatment in this case, whereby it prolonged the life expectancy of the canine patient by up to about 600 days or more in this particular case, further proving the efficacy of the treatment. More examples about the usage of survival analysis here. This is actually a survival table for the population of the United States in 2003. This is a table that insurers typically use in order to calculate premium. So in this particular case, the odds and probability of dying due to diseases and other natural causes are being calculated here. And this has a lot of importance to the insurance industry in particular, because it will allow the insurance industry players to calculate the viable premium to sustain the business while at the same time offer enough protection to the clients that are under their cover. So the same concepts can be extended to engineering sector. For example, how to manage the product life cycle. And this could also be extended in the mechanical engineering or various aspects of engineering as measure of mean time between failure. A time interval that is actually important, telling engineers when to maintain their machinery or when to exchange parts in the course of them performing preventive maintenance. This, on the other hand, is actually data from Department of Statistics Malaysia on the selected life table values for the Malaysian population. So you can see here in 2018, a newborn baby in Malaysia is expected to have an average lifespan of 75 years old. So that means they can live all the way to the year 2093. And of course, this can be further subdivided according to male, female, and due to all the types of differences in the types of risk and varying background that they are being subjected through. The MTBF over here is actually the extension of the concepts that I already explained earlier, mean time between failure, which is actually something akin to survivor analysis, albeit in the application of mechanical engineering field or various other fields of engineering that are looking at failures and preventive maintenance in order to minimize their impact. So having said that, what will be the relevant study designs for clinical and epidemiological studies? In essence, there are three: observational studies, clinical trials, experimental studies, which have been covered earlier, and meta-analysis, which will not be covered under this particular curriculum. So let's focus on observational studies. Observational studies can be further subdivided into 5, namely the case series, case control, cross-sectional studies, cohort studies, and historical cohort. So how do we look at all this classification of studies? As mentioned in the earlier video in questionnaire-based survey studies, you can see that cross-sectional studies is actually a snapshot, taking a snapshot in time of a particular population, whereas longitudinal studies involving a researcher taking multiple snapshots of the same subjects or body of subjects at different points in time, as being indicated here by this chart showing the direction of inquiry. Longitudinal means longitudinal in time, so you can actually look back in time or look into the future. Cross-sectional technically only means looking at the data at that particular point in time. So in case series studies, a case series report is a simple descriptive account of interesting characteristics observed in a group of patients. For example, unusual increase in respiratory syndrome and piglet mortality following the outbreak of respiratory and reproductive failure syndromes in sows. This eventually becomes a PRRS, which was first described around the 1980s and 1990s and formalized to become a disease beyond that particular point. And this is essentially describing certain characteristics of group of series of patients in the published report. In this case, since we're talking about case series, there are no control subjects, and this will bring about some challenges or some aspects of the studies which are being going to be questioned by the general masses. And since this case series studies is actually not planned, it may also not even have research hypothesis. So you need a much more robust study design to convince the general public or the academic community or the scientific community saying that there is actually a disease that is going on in the population now. Having said that, the main benefit of case series studies is that they can be used as hypothesis generating and general leads for subsequent case control, cross-sectional, or cohort study, which we are transitioning to now. In case control studies, we are looking at what happened to the population. It is being used to investigate causes and incidence of diseases and to identify risk factors. It begins with the absence and presence of an outcome and look backward in time to try to detect possible causes or risk factors of a disease of interest. And therefore, you have case control. So the cases refers to individuals selected for the presence of disease or a certain outcome. Remember, when we talk about cases, it doesn't really mean disease. It just means events of interest that you want to quantitate or you want to investigate. The controls are individuals selected for the absence of that particular disease or outcome of interest. And it is also important to make sure that the case and the controls are matched, because all comparisons should be done on the same footing, on the same comparative basis. Otherwise, there will not be any scientific justification to say that the comparisons is fair. And this case control studies is actually good to examine conditions that develop over time to investigate a preliminary hypothesis. And please do not confuse this with case series studies, which we're going to look at the later slides. And then again, since we're talking about case and control, and we definitely have to depend on high quality data, something that is actually of a rarer commodity when you are collecting data. After all, you may not really know what to expect when you are performing a study, and you may have overlooked certain clinical clues that is actually present in front of you. So sometimes generating high quality data from a series of observations could be a challenge on its own. Let's look at cross-sectional studies. This is actually an approach to investigate what is happening. It is used for disease description, diagnosis, and staging. It is typically synonymous with the so-called epidemiological studies, prevalence studies, and analyze data collected on a group of subjects at one time rather than over a period of time. So as I mentioned earlier, this is actually a snapshot in time. But sometimes people tend to call it prevalence studies because they tend to focus at one point in a defined time frame. Examples may include surveys and polls because surveys and polls are generally cross-sectional in nature. In this case, these cross-sectional studies typically will also allow us to stage a disease. For example, grades of laryngeal hemiplegia in horses affects efficiencies for gaseous exchange in lungs. And grades of laryngeal hemiplegia may be classified according to their grades. And these cross-sectional studies allow us to examine the usefulness of new procedures. For example, benefits of arthroscopy or surgery of shoulder on shoulder joint healing when examined under the MRI itself. However, having said that, even though they are good representation of snapshots in time, there are certain problems with representation, particularly in survey-oriented study, whereby due to the limited time frame, you may not be able to sample across the entire spectrum of population of interest. Next, which is actually being used to examine what will happen. Cohort is a group of people with something in common and remain part of a group over a period of time. Subjects are often grouped by predefined characteristics, and cohort studies are typically very, very valuable. For example, the famous Framingham study, which has started since 1948. It is being used to identify causes and incidence of diseases, natural history, and their prognosis, as well as the identification of risk factors. And method, it is actually a methods of choice to study causes of condition, time course of disease, risk factors, as we follow a group of subjects over time. And this also allow the advantage, the luxury of controlling biases, a very, very important consideration when you are formulating a study. However, cohort studies may require a long time to complete and oftentimes vulnerable to problems associated with follow-ups. And if let's say you have issues with patient attritions and patient migration, it will greatly reduce the effectiveness or the quality of data that you are actually collecting. And in certain cases, you may also need to contend with the issue of long time period between exposure and event of interest. For example, exposure to environmental agents and carcinomas, and the impact of commercial cat food against feline lower urinary tract disease. Both are events that will require extensive amount of time for us to really follow through our patients and until the development of conditions of interest. Historical cohort is actually a similar type of cohort studies whereby you group individuals of the same features. The only difference is that you are looking back in time. It is also known as retrospective cohort study. However, it is something that you really very much dependent on high quality data. And case studies typically begins by grouping outcome and examine the common attributes. And of course, to make it work, data quality is again a very, very important quality here. Something that is unforeseeable when we first start any other study. So having said that those are the 5 models that you can use for observational type studies, we need to determine the sample size. Relevant factors can be summarized in the following equation by Daniel, modified by Naing in 2006. So these will be the factors determining study sample size given by this particular formula here. Generally, precision is taken as 5% if the prevalence is between 10 to 90%. This gave a 95% confidence interval with of plus minus 5%. Or a total band variation of 10%. Precision is half to 2.5 if prevalence is below 10%, and adjusted to 0.5 multiplied by 1 over p, 1 minus p for prevalence higher than 90%. Do note that all these calculations very much depends on prevalence, as what we're going to see later. And of course, the same formula can be adjusted for a finite population as being given in this particular formula here. So in this case, it's important for us to adjust to the population because you may not be able to always accommodate the request for the number of sample size calculated due to the limitation in terms of the number of population. So in this case, this particular formula provides an exit or a way out or a solution for that. So having said all those approaches and the consideration of sample size, the common tools and traits and common tools of traits and terminologies of clinical epidemiology studies may include several things like 2x2 contingency table. 2x2 contingency table is something that is actually essential because it can be utilized for risk analysis, estimation of sensitivity, specificity of tests, and their respective predictive values. And these analyses, in turn, are the cornerstones of evidence-based medicine. So now let's look at risk analysis using a 2x2 table. Before we begin, we need to understand the fundamental terminologies. There are key differences between risk and odds. Risk actually denotes the number of events over number at risk. And it is actually a prospective measure looking forward into time. Whereas odds is actually number of times event occur over number of times events that does not occur. And it is largely a retrospective estimate. The only issue is that in a lot of scientific reports, we tend to report odds rather than risk. However, when we disseminate these results and information into the popular media often report the odds as risk. And there's actually one more issue about reporting all those values as odds, because odds tend to overestimate risk just because of the definition of these quantities alone. For example, if you have 100 subjects and 5 of them is actually susceptible to disease, the risk of having disease will be 5 over 100. However, if you calculate that as odds, then the ratio will be 5 over 95. 95 instead of 100 because we have already taken 5 out because the 5 has already had the infection or event of interest, whereas the other 95 do not have the event of interest. So as you can see here, obviously, the proportion of odds, the percentage of odds is of course much higher than risk. And for risk, the values range from 0 to 1, 0 for no risk, 0.5 implies equal risk, whereas more than 0.5 implies increased risk. Whereas for odds, 0 implies no odds, 1 for equal odds, whereas more than 1 or to infinity may indicate increased odds. Let's look at this particular example on the relationship between bovine mastitis and the sow milking machine. So what we can actually see here is that the vertical columns more or less tell us the clinical condition, whereas the horizontal rows tell us the exposure to the risk factors. This is actually an arrangement that everybody needs to remember, because for 2x2 table for epidemiological studies, you need to know that clinical outcome is always represented in columns, whereas exposure factors or risk factors is always represented in rows. So in this case, the risk of contracting mastitis after contacting the machine will be 130 divided by 310 based on the definition of 41 or 42%. Whereas the risk of getting mastitis, even though the animal did not come into contact with the swab machine, will be 10 over 110, in this case 9.1%. So the conclusion is that there is actually a higher chance of mastitis in the cows who came into contact with the swab machine. So When we talk about odds, and I've already mentioned just now, odds tend to overestimate risks. And it is also the point whereby a lot of popular media, newspaper tend to report odds. And odds is actually typically reported in scientific reports. Why? Because it denotes something that has already happened. So in this case, the odds of contracting diseases after contracting the machine will be, in this case, 130 divided by 180 instead of 310 as reported earlier in risk. So odds of getting mastitis, even though the person, the animal is actually not coming into contact with the salt machine, will be 10 over 100 instead of 10 over 110. So in this case, the odds will be 10%. And the conclusions are the same. Mastitis is actually more likely to happen in cows who come into contact with the salt machine. So the next question that we need to ask will be, how likely is likely? And this is actually where we do comparative qualities known as the relative risk and risk ratio and odds ratio. Risk ratio is actually defined as risk in a compact group over risk in a reference group. And the values range from 0 to infinity, where 1 is equal risk, less than 1 is protected against, more than 1 is increased risk of. And as you can see here, based on this, we can calculate the risk ratio, which is 0.419 divided by 0.091. It gives us a value of 4.6. It simply tells us that those animals that come into contact with salt machine tend to have 4.6 times more likelihood to get mastitis. When we transition to odds ratio, the concept of comparisons is also the same. But now we're talking about odds in a compact group divided by odds in a reference group. The range again is actually from 0 to infinity, with 1 denotes equal odds, whereas less than 1 denotes reduced odds, and more than 1 talk about or explain the situation whereby there's actually an increased odds. The more extreme the odds ratio go in either direction, the stronger the association between the risk factor and outcome. Remember, instead of the lower value, for odds ratio, we have a value of 72% divided by 10%, giving us the odds ratio of 7.22. Compare this to the 4.6 generated in the earlier calculation using risk ratio. Obviously, this is actually where I talk about odds overestimating risk. So next time when you read reports from popular media, remember that you could be reading the reports in odds rather than in risk, because odds are actually historical measure. That means refers to quantities that has already happened, versus risk, which is referring to the prospective quantities that has yet to happen. So how do we calculate the errors then? So the errors will be calculated based on this particular formula. And this particular formula will actually allow us to calculate the 95% confidence interval for the log risk ratio. And this is actually translated into the quantities, the range mentioned here, 2.3 all the way to 9.09. Bear in mind, in order for a risk ratio or the odds ratio to be significant, it must not contain 1. So in this case, the 95% CI for risk ratio is ranging from 2.3 to 9.09 and completely avoids 1.0. Why 1.0 is not considered inconclusive? Because 1.0 implies equal odds and equal risk in this particular case. So in this case, what we can actually say is that there's a significantly elevated risk of bovine mastitis when cow comes into contact with the salt milking machine. How to calculate all the risk? You can actually enter the data as what is being depicted on the screen here. And in this case, I'm actually using a method that is being used to key in the chi-square. So you can see here, you need one column for actually the clinical outcome, and you need another column for the risk factors. The third column will be the number of cases. So before you actually do this, you need to weigh data to assign and tell the computer that there are 130 cases of mastitis versus contacted salt machine, 10 cases mastitis due to non-contact with machine, and so on and so forth. Otherwise, it will not be able to give you the accurate representation and values during your risk calculation. So once you have put in all the necessary figures, and you then need to click on the statistics cell. So in this particular statistics cell, then you just need to click on risk in order to generate the risk profiles for all these parameters that you are looking at. And this will be the example output of the SPSS. Do note that the value in the risk estimate is the same as our manual count. So 4.6 is actually reporting about risk. 7.22 is actually reporting about odds ratio, whereas 0.6 is actually a more or less an inverse of this particular risk calculation. It simply tells you that if the animal did not come into contact with shot machine, it is protected against mastitis. And this, for this particular table, only values that are statistically significant will be reported. And how do you know they are significant? If let's say they are lower to the upper range, does not include 1. If it includes 1, even though you have a risk estimate value here, it is considered null and void. In this particular case, you can see 7.22 is actually valid. It's actually statistically significant because it is ranging from 3.6 to 14.4. Whereas 4.6 is also valid because it ranges from 2.5 to 8.4. On the other hand, 0.639 is also significant because it ranges from 0.571 to 0.714, and it does not encompass 1. So at any point, if the value encompasses 1, then that particular risk estimate or odds estimate will be null and void. Null and void meaning that there's actually no changes in terms of risk or odds, depending on whatever you're calculating. The next part will be in the use of 2x2 table for evidence-based medicine. So evidence-based medicine using 2x2 table can be used for all this.